All right. Hello, everybody. Let me check my settings really quickly. Looks like I'm good to go. Having some trouble with my mic here lately, but hope everybody's doing well. Hope you guys felt good about the Unit 2 test. I know that doing the practices and stuff, everybody looked like they were rocking and rolling with that material. That material is super important. It's the foundation to what we're going to talk about next. And hopefully my nearpod will stay where it's supposed to stay. All right, so coming up on this next unit is it's lengthy and it is a lot of material. So we're going to do our best to chunk this for you and to give you absolutely what you need to be able to be successful on that test and on the standard. So we are evaluating 1-5 and 2-1 throughout this unit. This is evaluate evidence of past and current movements, but then also formulating an argument to how first the internal processes of Earth are driving those changes that we're talking about in 1-5. And I really wish it would stop doing that. Sorry, hold on, guys. It's going to keep doing that because I was in preview mode, so I'm going to go restart this. All right, so maybe we're back with it now. Okay. At the end of this lesson, you will be able to, at the end of the entirety of this lesson, which will be broken up over 2 videos, but you should be able to evaluate the difference between continental drift, the theory of continental drift, and the theory of plate tectonics. Also, be able to connect the evidence that we talked about, fossil evidence, rock evidence that we talked about in Unit 2, to help build a rationale for plate tectonics, just like these scientists that we're going to talk about today did. And then identify the processes that form and modify Earth's crust. And again, these, it's like I love how beautifully laid out these concepts can be as they build upon one another. You know, we started with minerals. Minerals are the building blocks of rocks, and we moved to rocks. And rocks are the building blocks of layers, and layers move because of these internal processes, and then they modify and change Earth's crust. So it's beautifully laid out to build upon one another. And then we even go into further than that. We go into, well, then how do those things impact human life and human activity? Well, then we discuss catastrophic events such as volcanoes and earthquakes. So all of this information, all of it building up to this point is foundational, and this is even more foundational to what we're going to learn next. Nearpod's not loving me today, guys. We'll save that for class. All right. This is Alfred Wegener, and I know you just were like, what? If Wegener, you said a V, it's a Wegener. And yeah, you could say it that way if you want to. And you might hear some people say it that way, but he was German. They pronounce that W with a V, so Alfred Wegener is what I'm going to go with, okay? The very first theory of continental drift, or the idea of continental drift, was formulated by Alfred Wegener in 1915. Okay, think about mentality in that time and how rigid some of the places around the world were towards new ideas, especially in the scientific community. So it was not widely accepted at first, and we're going to talk about why. His only pieces of evidence were what we've already talked about when we did the Pangea lab, right? These continents look like they fit together. We have some fossil evidence. You were able to manipulate those continents to show how there could potentially be that fossil evidence there. And then we also looked at climate indicators and also rock indicators as well with that lab. So think back to that when we're talking through this. Alfred Wegener died in 1930 without ever seeing his theory come to fruition. We're going to talk more about why in just a second. Major points. these you do need to know. This would be a slide that I would screenshot, snippet, and file away in your Earth Science folder. Major points here: jigsaw fit of the continents. It looks like they fit together like a puzzle. Also the fossil evidence we talked about, climate evidence, and then rock evidence as well. All again going back to that Pangea lab. And you know, it would be really great if maybe at this time you kind of pause the recording and you pull that up and you look at, oh, and kind of remind yourself of what we walked through in class with that Pangea lab. So you could see it. You could see how we could manipulate, and I think this one's a little bit harder to do in that Pangea lab, but you can see how if we move these around enough, there's some similarity, and we could get it close, right? We could get it close. Sorry, I had to pause for a second. So you can see how these would fit together, just like a puzzle piece. The fossil evidence was very telling, right? We were able to move those continents around and kind of line up where those fossils were found across South America and Africa, India, Antarctica, Australia. Even further than the fossil evidence that we saw in that Pangea lab was the climate evidence. And with my students, what we did was we kind of fixed them all together, and then we went down and we selected climate in the evidence on that lab. And it was so cool to see that we got it, mostly right as we were fitting those pieces together. And so what we see here is we see that the climate in these different places has changed, and so that tells us that these continents were in different spots, different climate zones. And then we have the rock evidence, 250 billion year old rocks fitting together down here across Africa and the Appalachian Mountain Range, and then 450 million year old rocks across the Greenlands up there and Scandinavia. And those fit together. When we go back to talk about rocks, we go back all the way to minerals. We discussed that rocks have a definite chemical composition, kind of like we have a DNA. And that DNA, or crystal structure, chemical composition, means that these rocks had to be formed in the same place at the same time and under the same conditions. So that rock evidence is pretty good evidence that these continents were once together. So why did this theory not come to fruition before Wegener passed? Well, because Wegener was almost right. Wegener had a piece of the puzzle, so to speak. He didn't have the large part of the picture that he needed. And again, remember, the scientific community at this time, and it was hard pressed to get any new ideas through. So you had to bring it all to the table. And you would think, like, with all that evidence we just discussed, I mean, it's pretty, you know, pretty good evidence, right? With the fossils and rocks and climates, and but it still wasn't enough for them to accept it. Later on down the road, we have this guy named Harry Hess. Harry Hess ended up being a geologist, loved geology, found his love for geology in World War II. He was in the Navy, and in the Navy, he had the opportunity to use sonar out in the Atlantic Ocean. And what he discovered was that the tallest mountain range in the world is not Mount Everest. Matter of fact, the tallest mountain range in the world is the mid-ocean ridge, much, much larger than Mount Everest. So figuring out what was down there, like getting that opportunity to discover those kind of things must have been an awesome opportunity. But what Harry Hess discovered and coined the phrase of seafloor spreading. He discovered that in the Atlantic Ocean, all oceans in fact, but specifically this is where he discovered it, the ocean floor is moving apart. The crust itself is dividing all the way down to the mantle, and then that magma, that material, that molten material is coming up to fill that space. And what he got to study was how as we get further away from that mid-ocean ridge, those rocks get older and older and older until we get to the continents. So really what he discovered is how Earth recycles its crust, and particularly on the Atlantic side, how new crust is being formed. So this discovery, and with Wegener's discovery, so Harry Hess's discovery of seafloor spreading with Wegener's ideas, kind of put forth this idea of, okay, well, Wegener was almost right, but it's not continental drift. Rather, it's all of Earth's crust is moving. All of Earth's crust is moving, not just the continents. So at that point, we can't call it continental drift anymore. We changed the theory to plate tectonics. And this is a picture of Harry Hess, if you're wondering. We'll watch video clips in class and do that in class. All right. But why? Why are the plates moving? So Earth has layers, and that very top layer, the crust, and just below that, a semi-solid layer called the upper mantle. Those two pieces together are broken into pieces called tectonic plates or lithospheric plates. And those plates are moving, and they're moving because of the molten material underneath. You can see here, this is a great visual. I've used this picture for years when discussing the layers of the Earth. Look at the magnitude of interior Earth. Look how huge that molten material is, that magma in the mantle here. And let me annotate for you to give you. This is the mantle, and my, is it not huge? It's 75% of interior Earth. But also notice this over here. Oh, brown's an ugly color. Notice this over here. Look how thin Earth's crust is. Look how thin it is. It's like an eggshell. It's tiny. It's actually 1% of Earth. Just 1%. You're walking around on 1%. 1% is between you and magma, molten material. Pretty crazy, right? So it's very, very, very thin. And that's what we're talking about there when we're talking about that shell. That shell is broken into pieces called lithospheric plates. Again, we'll watch video clip in class. All right, let's talk about the layers. This is another slide that if I were you, I would snip it and put into my Unit 3 folder. So at the end, you have all of this essential information in one place as a unit review. The crust, we'll start there. The crust, just like the crust on a pizza is the outside, right? Crust is the outside. Some people don't like the crust. I think it's the best part. Prefer it over the pizza itself. But the crust is the outermost layer. It's only 1%. You need to know that percentage because you're going to be asked that question. What's the smallest layer of Earth? Okay. Then we have the mantle, and there are two divisions here of the mantle. And just like with any kind of organizational technique, there is a difference between the two, and that's why we have them designated as upper and lower. The upper mantle is semi-solid. If you can think about like Play-Doh or clay, kind of that consistency. And if you remember from the rock cycles and tie back in 2-7 here, that's standard. If you remember from the rock cycle, we talked about metamorphic rock, igneous rock. Those are under intense heat, intense pressure because they're coming in contact or close relations with the upper mantle, which is extremely hot compared to the crust. Thank goodness, right? So crust is cooler for sure. That molten material moves in the lower mantle, and you will not get away from this term convection for the rest of the semester. We talk about it so much, and we talk about it in many different ways. We're going to discuss convection in the atmosphere, which causes weather. We're going to discuss convection in the ocean, which causes those currents in the ocean. So convection is a hot topic in this class. But that lower mantle is that molten material. When you think of magma, you think of lava, that consistency. That's what we're talking about in that lower mantle. Then we have the core. The outer core is thought to be pure liquid rock, pure liquid, okay? And then the inner core is thought to be solid metal. And I would encourage you to pause this video for just a second and think about that. Why would we think interior Earth, we've got molten material, molten material, molten material, liquid rock, solid metal? Why would that be the case? So I encourage you to pause the video and think about that just for a second, mull over it. Two major concepts that you have to know before I even change this slide. Number one, density increases with depth. As we go deeper into these layers, and this is really intuitive, if you think about it, the heavier stuff sinks. Pretty simple, right? A lot of words mean something simple. The heavy stuff sinks. Makes sense, right? So your heavier material, like your metals, are going to sink towards interior Earth. They're going to sink towards that outer core and that inner core. So that's where we get that idea of metal. That's part of it. And then also heat increases. Scientists theorize that the inner core is as hot as the surface of the sun. Kind of blow your mind there, right? Hot as the surface of the sun, really? So as heat increases, right, that material sinking, heat increases, pressure increases as well. Just like we talked about in our rock cycle, bringing that back into play again, right? Those layers that are further down are under way more pressure than the layers at the top. Okay, so same thing here. So if we theorize that all that metal is sinking to interior Earth, right? Then we also have to think about what is that pressure going to do to that metal? And we think that it causes it to be solid. We think it's solid iron. Some people will say solid iron or nickel. And a lot of people theorize actually that nickel is more of what the outer core is made of, where the inner core is probably solid iron. I encourage you to pause the video and Google how we know, or how we have, I guess, developed this theory that the inner core is solid metal. You'll also come up with something else, and it has to do with our magnetic field. But we will talk about that a lot more when we get to astronomy, not quite so much right now. Okay. Also, when we get to earthquake waves, we'll talk about it there too. So, two things before I move: density increases with depth, heat increases with depth, and you could also even put pressure increases with depth, because that's a concept too. All right, we're almost there. Take a deep breath. Convection. I told you we were coming back to this word. The heating, rising, cooling, falling. I want you to say that over and over and over again. Say it in your sleep. Heating, rising, cooling, falling. Heating, rising, cooling, falling. Heating, rising, cooling, falling of molten material. We know this already. I'm sure that you have heard about heat, right? Heat rises, right? When you're in a house that on fire or something like that, you want to get down close to the ground. You know these things already. This concept of convection. I don't know if you've ever seen a lava lamp. How does that work? What about a convection oven, right? And so you've got that heating element, and then you've got a fan in there that is circulating that heat all the way around your food. So lots of examples. A pot on a hot eye, right? Why is it going to start bubbling from the bottom and then rise to the top? Well, that's because that is moving. The heat is rising up, right? Anything that's heated is rising up. As it rises, it's moving away from its heat source, so it cools. As it cools, it's going to fall back down. As it falls back down, it's encountering the heat source again, so it begins to rise. And this process happens in a circular pattern called convection. Interior Earth, inside the mantle, the outer core, we think, has convection as well, but we're really focused on what's happening in what we call the asthenosphere. That's the lower mantle. Okay, so you have the lithosphere, which is the upper mantle and the crust that are broken into pieces called tectonic plates. And then below that, we have the lower mantle, which we also call the asthenosphere, which is in constant motion, heating, rising, cooling, falling of material. That circulation is what's moving the plates. So if you could see me on camera, if we got, two cells that are going in opposite directions, then those two plates that are sitting on top of those cells are going to be moving apart, right? So if we have two cells that are coming together and they're moving this towards each other, and that would mean that the plates that are floating on top are going to collide. And sometimes this happens in, let's see if you can do it. Can you do it with your hands? Go like this, opposite directions. Sometimes we have boundaries where the plates meet that are moving side by side and they're sliding past one another. All right, that'll really lead us into the next lecture. So convection, major topic. We are going to talk about that all the way throughout the semester. Other key points: make sure you know each of these layers and density and heat. And I think maybe, yeah. All right, so that's where we're going to stop today. I think that's enough. Again, there was a couple of key slides on there that I would love for you guys to screenshot and put in your folders. Otherwise, I'll see you in class. Have a good day, guys.